the loading cap, and there's a coarse stone at the top and bottom, and there's the upper shear box and the bottom shear box, and for example, is placed between these two coarse stones. And when you perform the direction test, it's a little bit different, but conceptually it's the same. What do you measure during the shear test? What's the measurement? Force? What force? Shear force. There's a horizontal force actually, right? The horizontal force that's pushing this. Is it the bottom half? Bottom shear box or the upper shear box? Which one was fixed during shear? The upper shear box was fixed in your case, right? The bottom shear box was moving to the right side. That was forcing it. So you measure the horizontal force that's pushing this bottom shear box. And here, I don't know, I think the load cell has its variety of shape. So depending on the type of the load cell, on the resolution, on the price, or the range of the force, it has different shape. And this one is measuring the shear load, or you can say horizontal force. What about the normal force? Did you measure the normal force? So it's fixed, right? So that was the controlled variable. So you place a dead weight at the bottom, and that was applied to the normal force on the specimen, which was fixed. Right? It was constant over the course of the shear. And what was the other measurement? Did you measure the horizontal displacement? So it's called the LVDT, linear voltage displacement transducer, LVDT, and this measures the horizontal displacement. So actually it gives you a voltage value, but you can convert that voltage value to the displacement, like millimeters. And if you measure the vertical displacement, this is also for vertical displacement. So let's move on to the next page. If you look at the section, of the shear box, there's a normal force, and when you measure the delta T, in this case it's pushing this upper shear box is moving this direction, and the T is the horizontal force, and delta T is the displacement, and this is the horizontal force, and the vertical, the displacement of the bottom cap, not the bottom cap, the top cap, the loading cap, tells you the changing volume during shear. So if you measure the vertical displacement of the loading cap, it can be converted to the changing volume. If you have a volume change, then also you can convert it to noise ratio change. Okay. So that's what we're going to do. So steps are, first place the sample, apply normal load, and apply a shear load, and measure the vertical displacement delta A, and horizontal displacement delta L, and the shear force T. And you get this kind of curve. So if you plot the shear load versus displacement, you're gonna get this kind of curve, and the shape will be very similar. And if you divide the shear force with the area, I think there's also an equation for area correction, then you get the shear stress. Be careful because A is not fixed. A will change with the shear displacement. So there should be an area fraction equation. This is the displacement, so it's in millimeters or centimeter. Shear stress is in kilopascal or pascal or megapascal. Then the peak, you can select the peak point. So this is what? This is the maximum shear stress the soil was sustaining at this level of normal stress. Right? When you apply the sigma m1, which is at maybe 1 kilogram, right? And you can convert this 1 kilogram to the normal stress by dividing it with the area. Then you get the peak shear stress, right? And if you increase the normal stress, then shear stress will also increase because we run the how shear strength increases with the normal stress. So that's why the peak shear stress increases with the normal stress. So if you pick up this peak point for the maximum shear stress, you can plot it into normal stress versus the shear stress phase. You can plot these 3 data points, and if you linearize these 3 points, then you get the shear strength criteria or failure envelope. So this is the what we want to get, and this can be expressed with the molecular strength criteria. Or the C plus sigma n times 100 p. And at the same time, we can look at the shear behavior of the soil. In this case, delta H is the vertical displacement of the loading cap. So plus means that it gets dilated, so it's going up, and minus the negative value means it is what? Contracting or expanding? Contracting. Right? So this means that at the initial, it gets contracted a little bit. Then as you shear, it gets dilated or expanded. So we can see, we can look at the volume change graph or the vertical displacement graph and estimate the volume expansion. If it is positive value, if it is negative value, it's volume contraction. And volume expansion is also referred to as dilation in soil mechanics. Dilation. Okay, so I think in the lab report, you are required to draw this shear stress versus shear displacement curve, and also the vertical displacement versus the shear displacement curve, and the strength criteria. This is a failure envelope, the sigma n versus the tau curve. These three are already kind of paired. Okay. Any questions? This is okay. Let's read the notes and the advantages and disadvantages first. Notes. The first one, at least 3 tests are required to obtain strength parameter C and D. So actually, if you how many tests did you perform? The lab? 1 test? 3? 1 day left. Each group performed one test, right? Normal stress, how much was the normal stress in your group? Normal load, let's look at that. Yeah.
We are 10.
10 kilogram? What about the other? 2 kilogram? 2.5? What's the 5? What do you mean? What's the normal load? 1?
아니면 2.5kg, 10kg.
2.5 and 5 and 10. Right? So 3 of your group, 3 groups will share this result together, right? To get the strength criteria for the different 2 normal stresses. And this group also have the 3 different normal stress results. So at least 3 tests are required because the strength parameters are C and P, right? So at least you need to perform 2. Minimum 2 tests are required to get the linear line. But to be safe, the 3 are recommended. And the nominal area of the sample changes as the horizontal displacement occurs. So when you have a rectangular specimen and a circular specimen, you're going to have 2 different fraction procedure. And normal stress is the normal force over area, and shear stress is the of this direct shear test. Fast, simple, and inexpensive. So this direct shear test is very popular for obtaining the stress parameter of the coarse grain soil. So that way you don't have to consider the drainage or the water content or whether it's fully saturated or completely dry or etc. And good for dry coarse grain soil, and actually it's okay to use for saturated coarse grain soil. But disadvantage is difficult to control the drainage. We're going to talk about this, what the drainage is in the next class. Simply, it's control the water content. It's difficult to control the water content with this example. And the failure plane is forced to be horizontal, but in nature it could be vertical or with some angle, it could be diagonal, or because this is a little bit unrealistic. Stress concentration at the boundary can happen. So as you shear it, actually we are expecting the shear stress is uniform across the soil specimen, right, at the section. But in reality, at the boundary, the stress concentration happens. So shear stress can be higher near the boundary, and it could be lower the further in the further from the boundary. So that may occur, that may cause some error in the stress parameter. And the rotation of the principal planes and stresses occur. So this one will be examined with this figure. This figure shows the initial condition and the failure condition of the direct shear test. So initial condition, this is the specimen of the placed in the direct shear test box, and you have a normal stress, sigma 1, and sigma 2, and horizontal stress. So the initial condition will give you this kind of a Mohr circle. Okay? And here the pole will be here. And the horizontal stress is less than the normal stress because in this case K now will be less than 1. And at the failure, as it fail, maybe say the top is moving direction. And then soil element at this shear failure plane can be drawn like this, and you have a normal stress, sigma n, and the shear stress tau, and that can be expressed like this. Tau Ff and the sigma f. And when we, if this is a failure envelope, the deflection angle B, and sigma ff will be here, and tau ff will be here. So you can draw the Mohr circle that is tangent to the failure envelope. Then principal stress, where is the pole? This is the Mohr stress, and that Mohr stress is acting on the horizontal plane. That's the failure plane. So if you draw the line, the intersection with the Mohr circle, this will be the pole, OP, or the plane of the original plane. Failure plane is horizontal. So then, you want to find the major principal stress and the minor principal stress and the direction of major principal plane and the minor principal plane. Then, this is the minor and this is the major. Then if we draw the line like this, crossing this major and minor principal stress, and this line is parallel to the minor principal plane, and this is parallel to the major principal plane. Pardon me. So, major principal stress acting normally on this plane, and the minor principal stress is acting on this plane vertically. So, if we compare to this condition, major was here, minor was here, and as you shear, because you are forcefully making the failure plane horizontally, so this gets rotated. This gets rotated like this. So now this is going to minor, and this is. So during shear, that is one of the disadvantages of the directional test. During shear, major principal stress and minor principal stress rotates. So the planes are the shear behavior of dense soil versus loose soil. And dense soil, I prefer always like draw this kind of here. And if it's loose soil, more like tetrahedral convection. And when you have this kind of a densely packed soil, when you shear it, what happens? This particle will roll over. So it's going to go like this. So that in terms of the volume, does volume expand or contract? Expand, right? So volume dilation occurs. So as the shear displacement delta increases, the void ratio, what happens to the void ratio? Does it increase or decrease? Increase because the volume expands. And what about the density? Density decrease. So it's called the strain softening. Then on the loose soil, what happens? What about the volume? Volume contracts. Right? So as the shear displacement increases, void ratio decrease, density increase. So this is called strain. Delta is the shear displacement. So as the shear increases, okay, so as we shear more, void ratio decrease and density increases. So it's going to strain hardening. Because as you shear it, as you induce more strain, soil becomes more harder. So then we can draw the, this is a typical behavior, the shear behavior you can see from the dense soil. Dense soil shows a strain softening behavior with the peak shear stress. Like this. This is the tau versus the shear stress. So as you increase the normal stress, higher normal stress. As you increase the shear stress, the normal stress, the peak shear stress will increase, and also it's going to give you some peak point. And then it goes to residual state. So this is residual state. So then the volume change behavior. Initially we contract a little bit and then dilate. And as the normal stress increases, we contract more and then it dilates. Contract more and it dilates. So sigma n so the reason the higher normal stress suppress the dilation is as you confine more because you're applying the higher normal stress, soil is getting more difficult to expand. So that's why you get less dilation or less volume expansion during shear. The volume expansion is getting suppressed. Greater stress reduces volume expansion, and the example of this kind of behavior can be seen in the dense sand and the over-consolidated clay. So then, loose soil, we can compare the shear behavior to that of loose soil in the tau and the delta space. As normal stress increases, the shear stress also increases, but it doesn't give you like very distinctive peak. Doesn't have a peak. So you just need to pick up the maximum value here. Then it's going to give you the peak shear stress. And when we measure the volume change of the loose soil during shear, it just contracts. And as the normal stress increases, it contracts more. And what? In the soft clay or normally consolidated clay, you can expect this kind of behavior. And see